Hello, Math 1224. This is Dr. P with Lesson Launch 801. So now that we've done an entire chapter's worth of integration techniques, including how to integrate functions over infinitely long intervals, now we're going to shift our focus a bit to applications. And that's what actually most of the rest of the course is going to be, is how we can use integrals to solve other mathematical and real-world problems. And in this video, we're going to solve the problem of what is the area inside this semicircle, which has radius. I didn't put this in the picture, but it has radius r units. R, of course, for radius. So first of all, I want to mention a little bit of history here. This is a question that was, in fact, tackled by the ancient Greeks. The ancient Greeks considered the question of what would be the area of a circle whose radius is r. And their approach essentially was to chop this circle up into a bunch of little triangles. So they draw a triangle here, and then a triangle here. I'm just going to draw a bunch of radii. So they would start by drawing a bunch of radii. And they tried to draw theirs equally distanced apart. I didn't quite accomplish that here. But they drew a bunch of triangles, and they said, well, the area of the circle isn't exactly going to be the total area captured by these triangles here, but it's going to be very close. The triangles, if they're drawn correctly, all sit inside of the semicircle. So the sum of those areas of triangles, actually, let me just rewrite that. The sum of all these areas is going to be very close to the area of the circle. And in fact, if you let the number of triangles go to infinity, then those approximations will approach the area of the circle. That's how the ancient Greeks thought about this question. Now, in this video, we're going to think about it a little bit differently. We're going to think about it in a way that is a little bit more conducive to looking at this problem from a functions point of view. So the way that we're going to approach this, let me switch colors here. Okay. The way that we're going to approach this problem is we're going to slice this semicircle into a bunch of tiny little horizontal slices. So we're going to slice it like this. And the idea is we're going to be able to come up with a function that tells us what the area of each slice is. And then we're going to use an integral to add all of those slices up. Alright, so a typical slice is going to look something like this. And you'll notice that the width of the slices varies as we go from the bottom of the semicircle to the top. As we do this, the slices get shorter, or less wide, or whatever. So the goal here is to quantify how those slices are getting shorter so that we can write down a sum that gives us the sum of the areas of all of these slices. And then the idea is that if we let the size of those slices go to 0, or let the number of slices go to infinity, then the sum of the areas of those slices should give us exactly the area of the semicircle. Alright, so I'm going to clean up the picture one more time, because in order to do this, we need to do a little bit of geometry. Now this is always bad news for a lot of my students because thinking geometrically in this way is not familiar. So part of my goal in this video is to help you learn to think geometrically in a way that's conducive to setting up a function. So anyway, so the way that we sliced this figure was to slice it from bottom to top into horizontal slices that get shorter as we go along. So the question is, if we go from a height of 0, I'm going to call this a height of 0, to a height of, well, what would be that height there anyway? You have any idea what that height would be? Well, if you believe this is a semicircle of radius r, then that top height should be a height of r. And then the question then becomes, if I'm in a certain height, which I'll call y, actually let me change that a bit. If I'm at a height of y, from the bottom, y between 0 and r, then what is the width of the slice at height y? That's the big question here. All right. Now, here's where we have to use what we know geometrically. We know that this is a semicircle of radius r. We know that this height is at slice y. Now, one lovely bit of structure about semicircles that we can use here is the fact that every radius of a semicircle has the same length, including the one from the center of the semicircle here, from there to this boundary point here. So we know that that length is the same as the radius r. And I know that this length here, that's a length of y, because I said y was the height of the height at which this slice here is sitting. So the question is, what is the length of this segment here? And if I find that, then I shouldn't have any trouble finding the width of this slice, because it'll be twice whatever is marked by the question mark here, twice that length there. All right, but now what I see here is a right triangle, and if I have a right triangle and I know two of the sides, I can use the Pythagorean theorem to find the length of the other side. So I know that that width squared plus y squared should equal r squared. So that means that that width squared is going to equal r squared minus y squared, and therefore the width itself is going to equal the square root of r squared minus y squared. So what that tells us is that I'm going to try and keep the picture in the frame as long as possible here. I hope for the entire video, but I might not be able to quite accomplish that. Anyway, this tells us that, that the width of the slice at height y is 2 times the square root of r squared minus y squared. So if I draw this slice here, then its width is 2 square root of r squared minus y squared. All right. Now the next question is, what is the area of that slice? Well, the area of this slice is going to be that width, 2 square root of r squared minus y squared, times the height of that rectangle there, because that slice is a rectangle having positive area. It's not just a line segment. It's actually a rectangle with a width, which we've just found, and a non-zero but very small height. And that height is what I'm going to call delta y, because what we're doing is we're letting y change as we slice up through this figure, as we stack these horizontal slices on top of each other. I'm letting y change by tiny increments that I'm calling delta y. So the area of that slice is going to be 2 root r squared minus y squared times delta y. And then an estimate for the area of that semicircle, the estimated total area, is going to be the sum over some number of slices. I'm not going to mess too much with that part. I'm just going to show this part of 2 square root of r squared minus y squared. And of course, keep in mind that r squared, that's a constant throughout this entire process. Y, on the other hand, is changing. 2 root r squared minus y squared times delta y. And if we let delta y go to 0, then that estimate becomes the actual area, and that area is the integral of 2 square root of r squared minus y squared dy, and that integral runs from the bottom height, which is 0, to the top height, which is r. And this, once again, is an example of what I was talking about in one of my very first videos, which is we're taking this discrete thinking here, which gives an estimate, and we're turning that into an integral by letting delta y go to 0. Okay, so anyway, I could stop there and just say here's an integral which gives us the area inside of a semicircle. But it seems kind of unsatisfying to just let it sit there. We know what the area inside a semicircle should be. So why don't we evaluate this integral and see what happens? So I'm going to go ahead and evaluate that. Now this is a tricky one because I've got a square root of r squared minus y squared. I have nothing inside the integrand which lets me do a substitution of y squared. If I had a y out here, like a 2y or something, that would help quite a bit, but sadly I don't. So I'm going to have to use a fairly advanced technique here. It's one that you know of. You've seen it before. But I'm going to use a trig substitution. And I'm going to use a trig substitution to get y squared to equal r squared sine squared theta. The idea being that if I do that, this is then going to become, that's going to become r squared cosine squared theta, which I could then take the square root of and integrate. So anyway, if I let y squared equal to r squared sine squared theta, then I need to figure out what y is. It's not enough to say y squared equals. I need to know what y is. So I'm going to let y equal to r sine of theta. And then that makes dy, I have to be sure to replace that too. That's going to be r cosine theta. And by the way, I think this is one of those situations where rather than keep the limits of integration in terms of y and then substitute everything back so it's in terms of y at the end, I think I would actually rather just do the entire problem at this point in terms of theta. So to do that, I need to make sure and put my limits of integration in terms of theta as well. So let's think about how that's going to work. So when y is equal to 0, that's my lower limit of integration. When y is equal to 0, I think I can make that happen by having theta equal to 0. And if I want y to be r, then that could probably be accomplished. Now take a look at this. If I want y to equal r, then I need sine theta to be 1. So that means that I need theta to be pi over 2. So I'm going to have theta going from 0 to pi over 2 here. Let me just zoom out a bit so I can see what I'm doing here. Okay. So I think that my integral after the substitution is going to become the integral from theta equals 0 to theta equals pi over 2 of, 2 times the square root of r squared minus r squared sine squared theta, that really is what y squared will be, times dy, which is r cosine theta, d theta. All right, and now we have a little bit of algebra ahead of us. This is going to be the integral from 0 to pi over 2 of 2 times the square root of r squared cosine squared theta times r cosine theta d theta. And then you'll notice when we take the square root of this, that also becomes an r cosine theta. So we're just going to keep trucking along here. This is equal to the integral from 0 to pi over 2 of 2 r cosine theta times again r cosine theta d theta. And then that, now keep in mind here that I've got a factor of 2r here, a factor of r here, and r in this problem has always been a constant. I can pull all that out of the integral if I like, which I think I would like to go ahead and do. So it's 2r squared times the integral from 0 to pi over 2 of cosine squared theta d theta. Now this is a tricky one here. I don't know if we've ever talked about the integral of cosine squared theta. There is a standard technique for doing this, which is to remember the double angle identity. Cosine squared theta equals 1 plus cosine 2 theta over 2. That's a result of the double angle identity for cosine, is that cosine squared theta is equal to 1 plus cosine 2 theta over 2. And it turns out this, on the right here, much easier to integrate than this. This I don't know any straightforward way to handle. This one I can do pretty much visually. So that's going to be 2r squared integral from 0 to pi over 2 of 1 plus cosine 2 theta over 2 d theta. And then that's going to be 2r squared. And I think at this point I can just take the antiderivative, because that's 1/2, which means its antiderivative is going to be 1/2 theta plus, and then the antiderivative of cosine 2 theta is going to be sine of 2 theta over 2. I already have a factor of 1/2 here, so that's going to be sine of 2 theta over 4. And then we're evaluating at 0 and pi over 2, looking for the change in this function between 0 and pi over 2. Now the wonderful thing about this is, this part actually isn't going to matter all that much. When I let theta equal 0, this is 0. When I let theta equal pi over 2, well, this becomes a sine of pi here, because it's 2 times pi over 2. Sine of pi is also 0. So that works out just magnificently there. But anyway, I'm going to go and write down the whole thing so we have it in front of us. So we're going to have 2r squared times 1/2 pi over 2 plus sine of pi over 4 minus 1/2 of 0 plus sine of 0 over, oh, not theta, 0 over 4. There we go. And that's going to be 2r squared. And again, every term here, this term, this term, this term, all of those are 0. The only term that's not 0 is that. So we got 2r squared times pi over 4, which is pi r squared over 2. You might wonder about that too, but remember, we were finding the area inside of a semicircle, not an entire circle. So the answer to our question is the area inside of that semicircle is pi r squared over 2, or 1/2 pi r squared if you prefer. And we got that by doing horizontal slicing. Okay, now I should be historically honest here. This is not, I would not say that this is the real reason we know, like capital W, capital K, that the area of a circle is pi r squared, which is something that you could get from this. I think that we tend to defer to the Greeks on this one. The Greeks had a method for coming up with that area, which relies on pi being the ratio between a circle's circumference and its diameter. So what we're doing here is a little bit of a rewriting of history, but it's not a rewriting so that we're changing the facts. The fact is that the area inside a semicircle is still 1/2 pi r squared. It's interesting to see that there is a way of coming up with that using integrals. It was quite a bit of work, and there was some integration technique involved, but we were able to do it. Anyway, and that's the work there. I'm going to see if I can get all this in one frame. I probably shouldn't have spent the whole video going in one direction, but, well, anyway, if you want to see it all in one frame, there you go. In the next video, we'll talk about volumes. That's it for now.